help. Our goal with our webinars is to introduce our members to new frameworks and tools in the rapidly emerging technology landscape. And to do this, we bring top speakers from the world of tech. Today's webinar will focus on Completable Future. Asynchronous computation is an important requirement for any application today because there's a lot of asynchronous processing that happens for bulk actions, right? And in this webinar, we will take a deeper look at how we can use the Completable Future, which was introduced with Java 8, to achieve this functionality. And we'll also see how Completable Future has evolved over the years. How we can use it to compose different dependent queries and processes that can be chained. What benefits we get from it, and some of the risks that we could run into, and then how to sort of sidestep them or mitigate them fully. So this is a great topic. This is an area that is even the most experienced programmers sometimes are not very obvious, especially if you are from coding from a long time. Then you typically tend not to use asynchronous processing. You tend to avoid that as much as you can because you think it could create some integrity or reliability issues. But I think Computable Future sort of makes it really, really easy to kind of do that without creating any problems. And this, like I said, is a great topic. And to unpack it for us, we have a brilliant speaker. So we have David Gomez. He is a widely respected Java champion, and he is currently the developer advocate at Axonic. David has been working in software development for more than 20 years. He led projects for sectors as diverse as banking, defense, retail, maritime, and ground transport. David holds a computer science degree from the Polytechnic University of Madrid. He has been a central member of several tech communities, events, and conferences, both as a speaker and an organizer, mostly as a speaker. And currently, he is one of the organizers of the Madrid, Java user group, which is a very, very popular Java user groups around the world. And he is also part of the technical committee for Lambda World. So it's also a great functional programming conference, that happens in Cadiz and the south of Spain. So David, thanks for taking the time out to join us today. We're really privileged to have you do this webinar for us. Over to you.
Okay, thank you. Thank you for the introduction. Thank you for having me. And I'm looking forward to this session since some time ago that we started discussing about this possibility. Let me share my screen and let's go into it. So can you see my screen? I think so.
Yes, we do. Yeah.
Perfect. So basically what we are going to do is we are going to do a review of the different approaches that we had, the different support that we have from Java to concurrency constructs. And basically, we are going to review that history, and we are going to finish into one of the most powerful tools that we have today, which are Computable Futures. And basically, what I want to do is share with you today the reasons why you should be using Computable Futures, or the moments which are the benefits that we will get if we start using Computable Futures. If we get used to integrate Computable Futures, that's one of the tools that we have in our tool belt as Java programmers. It's not an easy one. It's a very powerful feature, but is also sometimes a little bit difficult to master. By the way, today what I wanted to do is take a more practical approach. We are going to see this historic version, how we arrived to these Computable Futures, but also I will share with you the benefits or why we use these completable futures, why we integrated completable futures in the library, in the framework that we are building in Axonic, and what we expected from that, and we are actually having, which are the benefits that we are getting from this. But let's start with a first definition on what is concurrency and what is parallelism, because sometimes these two concepts are used as if they were the same thing, but they are related, but they are different things. So the first one, parallelism, is something that we usually say when we have a lot of different tasks, but those tasks are basically the same type. They usually take the same time to compute. They are basically this kind of tasks that we find when we have a bigger problem and we split this big problem into a smaller chunks, into a smaller task. So basically, parallelism is what we do when we try to split this task among different CPUs or different computers. So we split the same task into smaller ones, but basically the same type of task is going to spread and send to the different CPUs. So basically the goal of parallelism is try to get the bigger task done before by sharing this workload among different workers. On the other side, what we say concurrency is when we face different type of tasks. So basically that means that we don't have exactly the same type of computing process in place. And in order to solve those tasks, we are going to apply different algorithms that maybe they are going to take different times to complete. So concurrency basically means that we are going to try to get all the benefit or to use the waiting times. For example, when we send a request to an URL, we are going to start waiting for that response. And that time that we are waiting, we are wasting CPU cycles that we could be using for solving some other tasks that are compute intensive. So basically, concurrency means that we are dealing with different types of tasks. And in order to put an example, just think like we are going to go outside of the IT world for a moment. Just think that you are working on a kitchen, that we are chefs or cookers, and we have to prepare the food for a big population or a big number of customers. And then we need to, in order to prepare the recipe, we need to do different steps, like we need to heat the oven, and we need to chop the tomatoes, and we need to chop the potatoes and peel the potatoes. So basically, once that we have the potatoes and the tomatoes chopped, we are going to put those on the oven. But for that, we need the oven preheated to a certain temperature. So basically, that means that when we are going to get the task of heating the oven or cooking the things that we have, the ingredients that we have prepared, our task means that we need to switch off the oven and wait until the oven gets the right temperature. So that's waiting time. So what we usually do is we start with the final task, which is basically cooking, by switching on the oven. And in the waiting time, we are going to probably get our people or ourselves to chop the ingredients and peel the ingredients. That's basically concurrency, because we are using the time that we are waiting for the task 3 to complete or to advance in order to deal with the task 1 and 2, which is chop the potatoes, peel the potatoes, and chop the tomatoes. So basically, but if you think that, for example, we need to use a big amount, we have a big amount of potatoes, a big number of potatoes and tomatoes to peel and chop, probably what we are going to do is we are going to ask some friends or some other workers to take some potatoes and tomatoes and do the same thing that we are doing. So splitting the load of chopping and peeling the tomatoes and potatoes among, I don't know, 10 cookers, it's parallelism. The fact that we are peeling and preparing the ingredients while we wait for the oven to heat to a certain temperature, that's concurrency. So basically, these are the different things that we are going to define, or the different concepts, how these two concepts are similar, are related, but they are slightly different. So coming back to our topic, Java and concurrency, Java had support for concurrency since the very beginning, since the very first version of Java. But the thing is that at that time, that even the computers were, most of the computers that we had were single core. They only had one CPU. Java already had support for concurrency and parallelism. But the very basic construct that is still in place today is the thread. That's basically the representation that Java and the JVM takes for the Java programmers to try to create different processes, different workers, and try to split the load between different CPUs. What we are going to do is basically we are going to create a new thread. We are going to start that thread with the task that we have created for that thread, and then we are going to wait until the thread has completed the task. But the problem is that with this very simple construct, creating a thread is one of the most expensive things in Java. Not only because creating an object is one of the most expensive operations, but because in this case, we are also creating a thread, which means that the JVM needs to synchronize with the underlying operating system and needs to create a process at the C level and needs to register that process with the CPU scheduler from the operating system. So creating a thread is really expensive. And sometimes the time that takes to create the thread and register that process on the CPU scheduler from the operating system takes, in fact, more time than actually creating the task. So sometimes threads were not used for tasks just because the tasks were more easily done in sequential, in just the main thread, than creating a new thread. But another problem that we had with this is that when we are creating threads, it's very easy to forget that we need to start the thread. This is a very common problem, a very common mistake that Java programmers that are starting to create concurrent programs fall into, which is, hey, I have already created the thread, I have assigned the task, so what I'm expecting is that the thread is going to automatically start working on that. So I forget about the .star method, invoking the .star method. And finally, the join call is what we use to know that the thread has finished doing the task and the task is already done. But that call is a blocking call, which means that the main thread is going to sit and wait until the thread is done. So sometimes when we created a thread and we started and we invoked the join method to wait that until the task is finished, what we were doing actually was waiting the same way that we would have if we didn't create the thread. So the next thing that we came up as programmers was this construct of the thread pools. With this basic thread tool, what we created is more complex objects which were basically hiding several threads that will basically look for any task that a client could have put into an internal queue. In that internal queue, the external clients will be submitting and putting the task that they wanted to be solved by our thread pool, by our worker threads. So basically, our task is added to the queue, and the worker threads are not directly just computing or solving the task that we are doing. Basically, in this case, our worker threads, the job that they do is basically they check if there's something to be done, there's something pending, there's any task pending to be done in the queue, and they get it. They get it, they execute it, and once they execute it, look for another task that could be, or they wait until some other client submit a new task. So basically, that's the way in which several clients could be submitting different tasks, and those tasks will be assigned or will be picked by the worker threads. The benefit of these thread pools is that the worker threads are not created on demand, are created at the startup of the thread pool, and they are kept working and checking on this queue of tasks that until someone puts a new task. So basically, the benefit of these thread pools is, the main benefit is that we are reusing the same threads, and we are not creating threads, which we saw that is one of the most expensive tasks that we could create. So in this case, it makes more sense to use concurrency or parallelism, because those threads are already alive, are already initialized, and submitting a new task, if there is a thread that is idle, will be immediately picked by them and executed. So that was basically the most basic infrastructure that we had to support concurrency in the first versions of Java. But then we had Java 5, and with Java 5, we had a lot of upgraded constructors. We had an improvement, a very big improvement of the concurrency and parallelism support that we had in Java. So basically what we had is new constructors. We are going to see one of several of them, but also new data structures that were specifically designed to keep in mind that they could be accessed by different threads at the same time. So they were optimized for this concurrency support. And this support that was highly improved after Java 5 has been revisited and has been improved in every version, in every new version of Java. And still it's improved today. So basically the next big thing that we are going to see soon, it's actually already there, you could start using it, is the new Loom project, which is hiding these virtual threads and some other improvements. So Java is something that Java is very seriously always supporting the concurrency. So starting since Java 5, we have new constructors that allow us to support running this type of tasks in an asynchronous way. The first one was the Executor Service. The Executor Service was basically a way of implementing those thread pools, but supported directly by the Java virtual machine. So with the Executor Service, what we could do is, there's another improvement over the threads, is that we can submit some runnables, some tasks that should be executed the same way that we were using with the threads, but now we can also submit something different, which is a callable. A callable is an interface that only has a method, but the difference with the runnable interface is that the callable is going to return something. The runnable is just a method of run that simply executes something and does not return anything. But with the callables, we are now allowed to submit tasks that are going to return some time of result. And in the case that we are returning something, the Executor Service is going to return a future, which is more or less a box in which the thread, the worker thread inside the Executor Service, is going to put the value once that they finish executing our task. But in the meanwhile, the client thread that has submitted that task or that callable to the Executor Service, it gets immediately a future, which is that box that allows him to keep the reference to the result whenever the result is going to be available. So the way that we work with Executor Service and Futures, it's just imagine that we have a long-running task that returns a result. This is a callable. And then what we do is we just create a new Executor Service. And for that, we have an interface, a class, executors, that implement some factory methods for us to create different type of thread pools or Executor Service in this case. In this example, I'm basically creating a new cat thread pool, which is basically a thread pool that is going to create new threads, new worker threads that they are demanded, but they are going to keep those worker threads are going to be kept inside the Executor Service alive, checking for new tasks. So in this case, we are getting the benefit of not recreating new threads every time that we submit a new task. We are reusing them. So this Executor Service now can be used to submit our long-running task that returns a result, and this is going to return a future. This future contains the value of the result, and we can ask for the value of that result, of that future, at any time. But the problem is that if we do that, the get method is a blocking call. It's going to make our client thread, the thread that submitted the task, is going to sit and wait until the future, until the callable is executed by the Executor Service, by the worker thread inside the Executor Service. So this means basically that we are going to be waiting and wasting CPU or cycles just waiting for the result. But the future also has another method, which is the is done, which allows us to know if the task has been resolved or not. But this is not a blocking call. This is going to return the result immediately. If the task if the callable has not been fulfilled, it has not been finished, we are going to return a false, and then we could do something else in our client thread, in our main thread. So that means that we are getting the benefit of the concurrency, because we could do something else. We could chop the ingredients while the oven is arriving to the final temperature. But that means that basically we can even now start running multiple tasks, because usually when we do concurrency is because we have a lot of things to do. So basically what we could do is we could basically submit all these tasks at the same time, and then again all the callables into a list or a collection, so that we could later on iterate over that collection to retrieve the results. But in this case, with this code sample, we are benefiting because we are able to submit all the tasks at once, and immediately after submitting each of these tasks, those tasks will be picked by one of the idle threads in the Executor Service. But once that we have submitted our threads, our client thread will sit and wait until the first task is finished, and we can start getting the results. So the first problem that we have here is, what if the first task that we have submitted takes a long time, takes, I don't know, 10 seconds to finish, but the second task takes just 1 second to finish. In this case, what we will be doing is just waiting 10 seconds until the first task has been solved, but we haven't realized that the second task is already there. and we could already be processing the results of the task 2 while we wait until task 1 is resolved. Luckily for us, we have another interface, which is the Completable Service, which basically allows to retrieve the tasks not in the order that they were submitted to the Executor Service, but in the order that they are finished, which allows us to do a little bit improvement over the waiting times on our client thread. We are not going to go into details of this Completable Service, but it's somehow related. We are setting the building blocks for understanding the Completable Service at last. So, but there's another problem. What if among all the tasks that we are submitting, that we are executing, they are not completely independent? What if the task 2 needs resolve of the first task as a source to start doing his work? In that case, the Executor Service is not going to help us because we need to submit the task 1 and finish and wait until that task is finished and get the result before we can actually submit the task 2. But the problem is, if we already know that we can change those different tasks, it would be nice to have a way to specify that when we are submitting the task, saying, hey, I need task 1 to be executed, and the result is what you need to provide as an input for the task 2. But we want all these tasks to be submitted at once and let whatever is going to take care of solving those tasks to change the results and provide the input for the task 2. And this is when and where Completable Future comes in. The Completable Future is another interface that was introduced in Java 8, and it has specific methods to submit tasks to an Executor Service. So the thing is that the underlying construct, the underlying object that is going to execute is a thread pool or an Executor Service, but we are going to have a different interface to provide these tasks so that we could change somehow how we want them to be executed. And that change, that way, is a Fluent API that is defined in another interface, which is the completion stage. That's the interface that allows us to submit the task, relating those tasks between each other, so that we could specify which is the input that should be, or where the input for a task should be taken from the result of a previous task. And there's also another fine thing that the Computable Future allows us to do, which is we can size differently the Executor Services, the thread pools, the number of worker threads that we are using under the hood. But let's go back to the first steps on how we use Computable Future. And let's think that we have this long-running task that returns no result. In this case, we have a task that returns no result. And in this case, the way to submit this task is a little bit different, because we are going to use the Computable Future run async factory method. In this case, providing the long-running task with no result to the run async method is going to return us a Computable Future. In this case, a Computable Future of void, because this task is comparable to a runnable, not to a callable. That means that it has a method which has a run, but returns nothing. So we get the Computable Future, and we can do something else. The benefit, because you could be wondering why the hell I will be interested in using a Computable Future, which is basically, or a future, which is basically a box to hold for the result of something, if that task is not going to return any result at all. The thing is that this way allows us to not get the result, but get use the same methods that Completable Future and Future has to check whether the task has been completely finished or not. So we can just simply invoke the get method, and even though that get method is not going to return nothing or is going to return void, we at least could wait until the task has been complete. It's a way of checking that. So this magic, the magic under run async, happens into the executor that the Completable Future is going to use by default. And this is basically implemented this way. The executor that is going to use, this is actually the method or the executor service, the pool that Completable Futures are using when we submit a task with run async, is they either use the common for join pool or they use a policy which is called new thread per task executor. So if in the case that they use in the common for join pool, the problem with Completable Futures is that the common for join pool is a pool that is shared across all the JVM. So that means that any piece of code that could be executing a run async method could be using the same thread pool. So this means that we lost a little bit of control of which are the thread pools, which are the executor service that are actually running our task, and which is the load, which is the number of tasks that our executor service are getting, because by using the common for join pool basically means that any piece of code, any line of code using Completable Future run async or any other process, any other submission to Completable Futures will be actually putting more workload on our for join pool. And actually, the common for join pool is also used by the parallel streams under the hood. So this is making the problem even bigger, because we may think that Completable Future is just taking care of our task, but is in reality taking a lot of workload. So that means that we could face the problem that whenever we submit a run async task, that task takes a lot of time to be resolved, just because there are some other parallel streams in some other parts of our code that are using the common for join pool. So this could be really a problem. But also the problem that our common for join pool has is that common for join pool is automatically sized. The number of threads that our common for join pool have by default is calculated in depending on the number of the CPUs that our computer has, and is using that number because the JVM thinks that any task that is going to be solved by the common for join pool is a CPU intensive task. But if we don't know that, we could be tempted to submit, to run asynchronously some tasks that are not CPU intensive. For example, we could use the run async, the Completable Future .run async, just to provide a list of URLs that should be checked with our remote server, for example. And that is going to make our threads in the common for join pool to wait a lot of time until the response are returned. And then maybe some other parallel stream that we have in our code is going to experience a very bad performance, because basically we are wasting CPU cycles of our threads from the common for join pool. And there's also another characteristic of these threads in our common for join pool, which is these are daemon threads, which means that if for whatever reason our main thread is finished, all the tasks that are running into the common for join pool will not be executed. So this is the things that we need to take keep in mind when we are using this simple run async method on the computable future. On the other side, there could be that the computable future or the JVM has decided to use the new thread per task executor, which basically the implementation is this one, is you are going to create a new thread per task and you are going to start the task. But that's bring us to the very first slide of our presentation. We know that this is not a very good way, because depending on the task, creating the thread and registering the thread into the operating system is going to take more time, or it could potentially take more time than the time required to solve the task. So we could experience the situation in which we see that running asynchronously our task is going to have a very bad performance compared to just executing that task on our main thread. So, but there's some ways to avoid this first problem. So, in order to do that, what we could do is we could just define our own executor service. And once that we have that executor service, provide that executor service to our run async method. That way, what we are doing is we are not using the default strategy, either the new thread per task or the common for join pool. In this case, we are making our computable futures to use our specific executor service that could be designed or could be sized or configured with the number of threads that we see that are convenient, depending on the type of task that we are executing and how much time we think that we are going to spend on waiting for network calls, for example. So this is a very best way to use computable future, but always providing our executor service, because at the same time we are going to be able to guarantee that our executor service is only used by the computable futures or in the places that we want to, because only those computable futures for which we have provided the executor service reference are going to use this specific executor service. So what if we have a task that returns a result, not our get running task that returns no result, but a task that returns a result? In this case, what we are going to use is not the run async, but we are going to use a different method, the supply assign method. This means that this is a small difference in the method, and this means that we are going to use a different method. And also the computable future that we are going to get is not a computable future void, it's a computable future of the type of result that our task is going to return. So that's basically it. The only difference is we either use the run async if we are going to use a runnable, or supply async if we are going to use a callable. And then we will get a computable future of void for a runnable, or a computable future of R, or the type of result, if we are providing a callable. So this is the computable future. And one of the things that computable future has is, of course, it implements the future interface, but also the completion states interface. And this second interface is a very important one, because this is where some of the nice features of the computable futures are defined. And this is the Fluent API that allows us to chain different tasks and combine the different futures. So let's see this with an example. Let's imagine that we are working on an online or an e-commerce store, and we are implementing the module that is going to receive an order and need to process those orders, just to know if that order should be processed or if there is any kind of problem. And one of the things that we need to do is, first, our module, our component, receives the order ID. So the first thing that we need to do is based on that order ID, we need to retrieve all the information from the order. And then another thing that we need to do in our process to solve or to check or to actually deliver the orders is we need to check for some information from the customer to see if that customer is not banned from our system or is or if it's a very important customer so that we could provide some discounts or whatever. But these two things, these two tasks are chained because in order to check the customer, for example, invoking another microservice or another REST API, in order to check the customer ID comes when we have the full information from the order. So we need to first get the order, and once that we have all the information on the order, we are going to check the customer. So the way that we should do this is we are going to invoke our order service and we are going to get the order. And once that we have the order, we are going to use the check customer to see if that customer is authorized or is banned, is allowed to place orders in our store. But this basically means that probably we are invoking two different microservices or two different modules or two different REST APIs to external systems. So this is going to take some time. And in fact, if I execute this takes 7 seconds to execute because we have very slow systems. So with Computable Futures, one of the things, we are not going to be able to get rid of that time because that's the order in which those should be executed. But one thing that we could do is try to compose and to submit the full list of tasks that should be executed from our main thread, and then we could go to do something else. And for that, we are going to use, or we could use, a couple of methods, then accept or then accept async. And we are going to provide the second task depending on chain to the first one. This is the code that we could use for the Completable Future to chain these two tasks. We are going to use Completable Future supply async, which is basically, this is a runnable, and the runnable is going to call the service and is going to return, it's a callable that has nothing and is going to return the order. So we are going to supply async this task that is going to return an order. And then we are going to configure a second task that is going to receive as the result the object that was returned by the first Completable Future. The first Completable Future, the supply async, is this supply async is going to return a Completable Future of order. And then the then async is going to consume that order. So we are chaining in the main thread the task that we are going to execute. And we don't have to actually check for the first task to be solved before doing this. So actually what we could see here is that the main thread has executed this concatenation of chains very quickly, which is basically sending this task, and then the different tasks, the get order and the check customer, more or less roughly takes this 7 seconds, but they are run completely asynchronously without the main thread having to check to be checking on when the first task has been solved. But there's also some other scenarios, like, for example, what if I have two tasks that could be executed in parallel after getting the order? For example, let's say that we have this check customer, but we also need some reports or some statistics to fill, and we need to send that information with the order to track activity. One thing that we could do is we could also chain this task in that way. We are going to provide the first task, which is this Completable Future supply async order service get order. This is going to return a Completable Future of order. And then with this completable future of order, we are going to concatenate two different tasks that will be executed at the same time. Once that we have the order, once that we have the first task solved, we are going to invoke at the same time these two tasks. One is going to use the activity tracker to check that the order has been processed, and then is the second one is going to do the customer check. So in this case, we could see that the main thread has immediately submitted the task, and then the worker one was getting the order, and worker 2 and worker 3 were working in parallel to provide the activity tracker and the customer checker. There could be some other scenarios. What if one of the things that we need to do is we need to check the customer, but also we need to check with the warehouse or with the inventory service if any of the products included in the order have availability, if we can provide those. In that case, we could find that we are going to take, like, I don't know, 5, 4, 10 different checks that could be executed in parallel. But we don't know how many of them until we get the information on the order. Well, we can also do this using Computable Futures. This is going to be a little bit more difficult to read, but I'm going to provide you the slides so you can go with over this later on. But basically, the first thing that we are going to do is we are going to create our first Computable Future that is going to return our Computable Future of order. And then on one side, we are going to create the customer checker over the order or the Computable Future of order. And then what we are going to do is over the same, this is a mistake, this is order CF. We are going to create another task that is going to basically check the order, and it's going to create a stream for each one of the items included in the stream. And that stream is going to be mapped, is going to be converted into something that is going to provide a completable future. And that completable future is going to check, or it's going to create as many completable futures as products we have in our order. So for any of these completable futures, we are going to run in parallel this task that is going to check the availability. We are going to collect them, and once that we have collected them, we need to check that all of them have finished, so we invoke the Completable Future join method. This is a little bit more complex, but it's technically possible to create these complex workflows of Completable Futures. So this is very powerful, and Completable Future has a lot of ways to combine and chain different tasks depending on the results and how we want to combine them, or if we want them to use the same executor service or different executor service, or use the same thread that the previous task was using or not. There are a lot of things that we could do. And for that, we have a good bunch of different methods. But mind your head, this is really powerful, but watch out with this, because some of these methods may have some tricky behaviors or may not do exactly as you think at first. So the best advice that I can give you is that it takes some time to explore the API, to play with these completable features and how they are chained. But in the end, if you master this completable feature, the time and the powerful that it brings, it's worth it. So, but let me go into a different thing, is how, because this is using completable features as a customer, as a client. But in our case, in Action Framework, and I'm going to try to give you a little glimpse of a little overview on why we consider using computable futures, or why you should consider using computable futures when you are actually building a library or a framework. If you are writing a library, you could also consider to return computable futures from your methods, because that way you could enable your users, the developers that are going to use your framework or library, to change this method and get all the benefits of using computable futures, while you, as the writer, as the author of the library, keep control on which are the executor service, the thread pool that are going to be used to execute your task. And this is very important, because otherwise you could face the problem that someone externally is trying to call your methods using a common forging pool. But if you directly return the computable future, you are in charge to create that computable future. And that means that you could potentially, or you will probably create or define the executor service that you are going to use. And there's some other frameworks like Spring or Tomcat that are going to benefit of handling computable futures. So if you want to do this, you need to create the computable future by yourself. You can always create your new computable future. This is going to give you the box in which you will place the result. But that computable future is going to offer to the client, to the consumer, to the developer that is using your framework or your library, the methods that we have already seen to check if the future is done, to get the value of the future, or to compose the different tasks. And you, as the producer, you can at any point invoke the method complete or complete exceptionally to communicate that you have finished the task and the result is available. And I'm going to here to introduce how we use this at Axon Framework, or why we use this at Axon Framework. But for that, I need to probably give you a little bit of context of what Axon Framework is. Axon Framework basically is a framework, a Java framework that is, it works either with Spring on top of Spring Boot or for regular Java applications. And it's very useful for cases in which you want to create monoliths that are modular, that could be split into microservices or split into different modules very easily. But Axon Framework always thinks that you are using CQRS, command and query responsibility separation, that you are using also event sourcing as part of an event-driven architecture, and you are using DDD as the way that you are designing your system. If you are using those, which for a complex project, I recommend you to, Axon Framework is very useful and will make very, very easy for you to create all the components that you need. So in our case, we have support to define commands, queries, and how the command model and the projections will synchronize by using events. But in this case, for the point that in which we use the computable futures is for the part in which the controller is going to send a query message to retrieve some information. And for that, Axon Framework and Axon Server defines a query bus and handles by you all the details of creating the query message, putting that query message on a query bus, and that query bus sending to a handler that is going to retrieve the information and with the results back to the controller. And those could be different modules running in different microservices in different machines. So the way that we have implemented this query bus implementation is using computable futures, and we are offering computable futures to the writer of the controller. So in this case, basically, our query method is the version that I'm going to show you is a little bit simplified, but it's more or less correct. So what we are doing in our query message, in our query method, we are basically creating a computable future with the query response message, and then we return that as the query transaction. If we, during processing this this query, which means putting that on the bus and then getting response or invoking the handler, we have some kind of exception like connecting to the action server, we will complete the completable future exceptionally to know the user, to let the user know that there has been an error. And basically here is how we are how we are processing. In this case, we are using the action server connection manager to connect to the server, to the query bus implementation, and get this message, put this message into the server. And then this is basically, we are using a result stream, which means that this get connection query is handling asynchronously the threads, the resolution of this query. And basically what we finally do is when we have the result available, we finally complete, we mark the completable future as complete, providing the result that was returned by this connection manager. So basically this is it. The three main things here is that we have a query transaction, and that query transaction is the first thing that we are going to return, which is a completable future. And then if there is any kind of exception, we have the ability to, after returning the query transaction, complete that exceptionally, and then complete the message asynchronously when the thread, this code, is going to be executed by a different thread. So this is basically the way that more or less we have used the implement. Which are the benefits? The benefits is that whenever anyone using Action Framework is going to implement the controller, the REST controller that is going to invoke our query gateway, basically we are just asking them to provide the query, the components, the task that is going to be executed, the message that is going to be sent, and we are returning a completable future. And the funny thing is that they could either use this to concatenate different queries that should be sent to different messages, which is not an usual case if you are doing DDD properly, but also you can return in the Spring Boot REST controller, you can return the future. And that means that Spring Boot is going to be able to manage Tomcat connections much better. So I'm going to skip over this because it's basically what I have done, and I want to show you a little demo on how this is working, on which is the benefit of this. For that, I'm having here basically a slow controller. Perfect. This is a slow controller, which is basically has two endpoints, the slow sync and the slow async methods. Basically, both methods are going just to try to solve a task, which is a task that takes 1 second to solve. This is a very easy way to solve. Are you seeing my code, right?
Yes, we can. Yes, we can.
Okay, perfect. So basically, I have two implementations. One has a new fixed thread pool, which means that I'm creating fixed threads. So I'm controlling how many threads I'm using on my side. But also what I'm going to do is I'm going to start and I'm going to configure, just in order to show more clearly, which is the way I'm going to configure the number of threads that Tomcat is using to 1 instead of the 200 threads that Tomcat usually use. I'm going to put this down to 1 so that we could see what happens if we overload the thread pool of Tomcat. So in this case, I'm going to start first. I'm going to start the servers. And then I'm going to start, servers will be starting, there we go. And then I'm going to start my application. Okay. And then what I'm going to do is, or I'm going to do this through a terminal. Let me check if I have one here. There we go. I'm going to put this here very quickly. And basically, here I'm going to use a tool which is called Hey, which allows me to simulate several requests at the same time. So I'm going to say that I'm going to invoke, I want to invoke like two concurrently, two requests to HTTP, localhost 10,000, 8080, and I'm going to copy the URL. And then I can see that the first, because I have just one thread in my Tomcat pool, the first task is going to execute in 1 second, but the second task needs the first task to be executed first and then execute. So it takes 1 second that takes the task to solve, but another second, which is the second that needs the first task to solve. If I do this for a higher number, if I do this for 50 requests, it's going to take a lot of time, because the last request is going to have to wait until all the Tomcats, all the thread pools, all the threads in the worker threads in Tomcat have solved the previous task. But in this case, let's, for example, use 10, and we are going to see that more clearly. It's going to take some more time. The process are being received here, and this is the thread by Tomcat that are handling the request one by one. And we can see that the last request has taken 10 threads to solve. But if I use the other endpoint, which is basically using a Completable Future supply async to execute the task, and then is returning the Completable Future itself, this is going to make Spring to get use of that, and is going to release the Tomcat worker first. So if I do this, even doing the same thing, I will see that the fastest task was solved in 1 second and 83 milliseconds, and the slowest one, were 2, were solved in 1 second and 100 milliseconds. So this means that I have unloaded the load of the worker of solving the task, and this task is being solved by my own pools, my own threads, not the threads by Tomcat. So this means that actually I'm getting the benefit of solving this better. So as we are approaching the end of the talk, I'm going to jump very quickly into the conclusions. So basically, my conclusions is that Completable Futures are very powerful tool to compose and combine and execute different tasks. But it's always better to use your own Executor Service instances in order to avoid the common problems of using the common for join pool or the new thread per task strategy. And also, you need to master and to be aware to try to practice a little bit the different concatenation talks. I'm actually preparing a second talk that is the complementary talk to this, in which I could offer some of the problems, some of the details of the problems that some of these combining methods have. And also, if you are writing your own framework or your own library, consider always not only using the completable features to solve your internal task, but also providing completable futures as the type of result of your framework and library. So this is basically it. I have prepared a little bit of a landing page in which I have collected some useful information. The first thing is the slides, also a reference to the Java Concurrency in Practice book. Also, it's very interesting if you are interested in concurrency things. You could, if you don't know, the Java Specialist newsletter is written by Dr. Hein Kabut. He's another Java champion, and he has been writing about advanced Java topic for a long time, especially about concurrency, but also on performance, on performance and GVM tuning. And it's definitely it's very well recommended. He also offers some courses, some specific courses on concurrency. And if you are curious, even though it wasn't the main topic of the talk, if you are curious to know a little bit more about Axon Framework, you have a small tutorial. If you are into microservices on how event sourcing and event-driven architectures could be implemented very easily, this is probably something that you will be interested in. That's basically it. This is if you scan that QR code or if you point to that URL, you will get a landing page, and I have listed all the resources that you could get. So that's basically it. I don't know if we have time for any questions, or if there's any questions, I'm happy. If not, you can also reach out to me by Twitter. My Twitter handle is this one, DJOMEZJ G. So that's basically it. If you want, I'm more than happy to answer any questions that we may have.
Right. Well, thanks a lot first, David, for a brilliant session. In fact, starting all the way from the thing that confuses people, right? So concurrency versus parallelism versus asynchronous execution. So I think that's something that's not very clear to most people. I think departing from that point onwards, and I think your whole presentation that sort of took us through the really amazing way in which the whole thing evolved, because I didn't expect async to be so easy, right? So in Java, you could do that very easily in Node, but in Java, to be able to do this is really a powerful feature for most developers. So thanks for doing this session. Very enlightening, very hard, clear-headed, focused, and hands-on. And typically, one of the questions we generally get at the end of these sessions is, where do I go looking for resources? But you sort of bet me to it. You already, have a slide for that. So we'll not have any time for questions. But yeah, I mean, like you said, I'd encourage people on this call to reach out to you on Twitter. But would really want to thank you from the bottom of my heart for a really interesting session. I have learned quite a bit from it today myself.
I'm glad that you found it useful, and I'm very happy to help anyone that reaches out to me. So I will do.
Yeah, thanks a lot. And then we would hope to bring you back for another session sometime in the future as well.
I will be more than happy to join you again.
Yeah.
Thank you.
So thanks a lot. Yeah, have a good day. Bye-bye.
Bye.